In the last two lectures, we discussed about the sinusoidal oscillations and the oscillatory circuit or tank circuit. And also we have discussed about the how we can produce undamped oscillations from a tank circuit. The important things which we should not when producing an undamped oscillation from a tank circuit is that we should provide sufficient amount of energy to the tank circuit so as to meet the losses in the tank circuit and the AC energy removed from the tank circuit by the load. Also, we should be careful about the frequency of the applied energy and also the phase of the applied energy. The applied energy should have the same phase and the same frequency as that of the oscillations produced in the circuit. So here, if we consider a circuit of the amplifier with a positive feedback as shown here, just we are given a schematic diagram. Here it is having an amplifier circuit here and a feedback circuit, and a signal source is connected here, and the signal is connected to the amplifier through a switch S. Suppose this is a switch. When the switch is closed, we know that the input signal appears across the input terminals of the amplifier, and if it is a common emitter transistor amplifier, it will produce a 180-degree phase difference of the signal, and also it will be amplified. So we will get an output voltage like this. That is, there is a 180-degree phase difference between the output voltage and the input voltage, and also the output voltage is amplified, or the amplitude of the output is greater than the input, and it is usually given by V out is equal to AB into V in, where AB is the voltage gain of this amplifier. Now a feedback network is also provided in this circuit. That means a part of this output voltage has been fed back to the input through a feedback circuit. Here one of the important thing is that the feedback network also produces or introduces a 180 phase difference. So when we take a fraction of this output voltage and makes a 180-degree phase difference, then the feedback voltage VF will be in phase with the input signal and is given again to the amplifier, and this is a closed loop circuit, and the circuit gives a particular closed loop gain, let's say AVF. Now this circuit cannot be treated as an oscillator, because according to the definition of the oscillator is a device that converts DC energy into AC energy, but here we are having a AC signal applied here, so it cannot be treated as an oscillator. That means an oscillator does not have a signal source, or signal source means there is no source of AC signal in the circuit, but this circuit does not qualify it as an oscillator because of the presence of this input signal. Now if we remove this input signal by opening the switch S, for that consider this diagram. The switch is opened. That means the input V in is removed from the circuit. The rest of the circuit is this one. So the amplifier is here, there is a feedback network is here. A part of this output energy is fed back to the feedback, and that means a feedback VF is applied into the input of the amplifier. So this circuit is having an input voltage which is given by VF, that is the voltage provided by the feedback network. So this circuit will serve as an oscillator. Just we given a trigger, initial trigger to the amplifier, so we get an output voltage, and part of output is fed back to the input signal. Then we are removing the input voltage signal source, but there is a VF voltage is fed to the amplifier input, so it is amplified and we will get an output voltage. So now this circuit does not have any AC signal source, but still it provides an output voltage. So we can say that this is a circuit with a positive feedback, an amplifier with a positive feedback serves as an oscillatory circuit, but we need a trigger to start. Usually this triggering is achieved not by using a signal source, but by using an oscillatory circuit. An oscillatory circuit, to produce oscillation, just we need in the case of an LC oscillator, we need the capacitor to charge to the maximum initially. That is achieved by using a battery. A capacitor is charged by connecting to a battery or a DC source. So the electrostatic energy stored in the capacitor produces oscillation. That oscillation can be connected to the amplifier circuit, so the amplifier amplifies it, and a part of this is output is fed back to the input, and this feedback network is again connected to the oscillatory circuit to meet the losses. So when we connect an oscillatory circuit here or a tank circuit here, then it will act as a perfect oscillator. Before discussing the oscillatory or how we can produce this oscillatory circuit or schematic diagram of an oscillatory circuit, just consider an amplifier with positive feedback. We know that the gain of an amplifier with positive feedback is given by AV divided by 1 by MV AV, where AVF is the closed loop gain, AV is the open loop gain, and MV is the feedback fraction. This is the case of a positive feedback. For negative feedback, we know that this is 1 plus, so that the total gain is decreased. But if we consider that usually the gain of any circuit is given by V out divided by V in, the output voltage divided by input voltage. Here it is AV divided by 1 minus MV AV. But in the oscillatory circuit, for oscillator, V in is equal to 0. That gives, this implies AVF is infinity, or it is ideally we can call it as infinity, but it is very high. So if AVF is infinity, according to this part, V in is equal to 0 gives AVF is equal to infinity. Then using this equation, in order to make this equation infinity, 1 minus MVAV should be equal to 0, or MVAV is equal to 1 is the condition satisfied by an amplifier with positive feedback to produce oscillations. Or to act an amplifier circuit with positive feedback as an oscillator, the condition that must be emphasized is given by this one, MVAV is equal to 1, and this criterion or condition is called the Barkhausen criterion. So this condition is called Barkhausen criterion or Barkhausen condition. MVAV is equal to 1. So let's summarize the things that how a an amplifier with positive feedback can be used as an oscillator. A transistor amplifier with a proper positive feedback will work as an oscillator, that we have seen. And also the circuit needs only a quick trigger signal to start the oscillation. Once the oscillations are produced, it will continue indefinitely if we provide the proper feedback. That is, once the oscillations have started, no external signal source is needed. I told you this is achieved by using a tank circuit. So the initial triggering is achieved by using an oscillatory circuit or tank circuit. And also another thing is that it should meet the Barkhausen criterion, that is MVAV should be equal to 1. Now let's go to the essentials of a transistor oscillator. That means we have seen that an amplifier with a proper positive feedback can serve as an oscillator. So let's discuss about the essentials of a transistor oscillator. I told you a transistor oscillator will have a tank circuit or an oscillatory circuit to produce the oscillations or to start the oscillations. This is achieved either through an LC circuit or through an RC circuit. We have discussed how an LC circuit can produce oscillation. In a similar way, the RC network can also produce oscillations in a circuit. So we can use either an LC network or an RC network to start the oscillations from a DC source, or by using DC energy we can start the oscillations in a circuit by using an LC or RC network. Then this is given to an amplifier circuit, and here it is an LC circuit is shown in this diagram. Here this LC is, suppose the capacitor is initially charged, that is, this capacitor is connected to a DC source, the capacitor will be charged to the maximum value, and this LC network will produce oscillation. That oscillations will be amplified by the transistor amplifier. So the oscillatory circuit is connected to the input terminal of the transistor amplifier. And the frequency of oscillation is actually given by, if it is an LC network, then it is F is equal to 1 by 2 pi root LC. The frequency of oscillation of a RC network, that we will discuss while discussing the phase shift oscillator, another type of oscillator. So just remember, for an LC circuit or a tank circuit containing inductor and capacitor, the frequency is given by this one, and these oscillations are given to the input terminal of the transistor amplifier. Now another thing is that we have to produce a feedback, positive feedback, so we will use a feedback circuit. The output of the transistor amplifier is connected to a feedback circuit, and the feedback circuit is again connected to the tank circuit in order to meet the losses in the tank circuit. So once the oscillations are produced by this tank circuit, it is amplified and obtained in the output of the transistor amplifier. A part of this output is given to the feedback circuit, and which is fed back to the oscillatory circuit to meet the losses, so that this process is continue indefinitely. So we will get a undamped oscillations in the output of this transistor amplifier. So this is the general or a schematic representation of a transistor oscillator, or the essentials of a transistor oscillator. They are a tank circuit to produce the oscillations, an amplifier circuit to amplify the oscillations produced by the tank circuit, and feedback circuit to meet the losses of the tank circuit. They are connected in this way, and we can get an undamped output from this oscillatory circuit. Now let's discuss about the different types of practical transistor oscillators. I told you either we can use LC network or RC network to produce the oscillations, and we have discussed about the LC network. We will discuss the RC network later. Before that, just we will introduce you some of the different type of transistor oscillators. Remember that all the oscillators under different names will have the similar function, that is, they produce continuous undamped output. However, the major difference between these oscillators lies in the method by which the energy is supplied to the tank circuit to meet the losses. That means the method of providing the energy to the tank circuit to meet the losses will be different for these different circuits. So just let's recall the circuits, different transistor oscillatory circuits. One is called a tuned collector oscillator. There is a tuning circuit is connected in the collector. Tuning circuit means an LC circuit is connected in the collector of this amplifier circuit, which will produce the sustained constant oscillations in the output, which is called a tuned collector oscillator. Another type is the Colpitts oscillator. Another is the Hartley oscillator. All these three are LC oscillators, and which serves to produce the frequencies from 10 kilohertz to 100 megahertz. All these three can be used to produce the oscillations having the frequency ranges between 10 kilohertz to 100 megahertz, and all these three, the tuned collector oscillator, Colpitts oscillator, and Hartley oscillator, are the LC oscillator. The phase shift oscillator is a RC oscillator, or the tank circuit is an RC network in the case of a phase shift oscillator, which produces frequency ranges from 1 hertz to 10 megahertz. And another one is the Wien-Bridge oscillator. Wien-Bridge oscillator is not discussed in our syllabus. Anyway, it is also a RC oscillator, or the tank circuit of a Wien-Bridge oscillator. Wien-Bridge oscillator contains an RC network which will produce frequency ranges from 1 hertz to 1 megahertz. And another one is the crystal oscillator. Crystal oscillator produces a fixed frequency depending upon the crystal itself. You may be heard about the quartz crystal. When a stress is applied or electric current is applied, it will have a stress and it produces frequencies, and such crystals can also be used to produce oscillations, and they are called the crystal oscillators. All these types we will discuss in the upcoming lectures, except this Wien-Bridge oscillator, since it is not mentioned in your curriculum. Remember that these LC oscillators are usually used to produce the oscillations in the high frequency range. They are not used in the low frequency range, because you know that the frequency is F is equal to 1 by 2 pi root LC. In order to produce low frequency, F to be small, L to be very high. In order to make high inductance, the winding or the inductor will be very bulky, so we cannot produce very portable oscillators for small frequency ranges when we are using LC network to produce the oscillations. So in order to produce low frequencies, we will use the RC network. So we will discuss about the different type of oscillator in the coming lectures. So that's all about the introduction to oscillators and oscillatory circuits. Thank you.